All right, we're right at the hour, so we'll get started. Good morning, good afternoon, everyone. Thank you so much for joining our first 3LC webinar. We're very excited to have you here. Today's webinar is Wildfire Datasets, Pruning Redundancy and Fixing Labels in 3LC. Our presenter, Copeland Lores, who's one of our data scientists, will demonstrate how 3LC helps teams identify redundant wildfire imagery, correct ground truth labeling errors, improve model performance with smaller, higher quality data sets. If you have any questions, feel free to put them in the chat and we'll be sure to answer as many as we can at the end of the session. And also, if you'd like to learn more about 3LC, just simply click the Book a Meeting with 3LC to learn more button at the bottom of your screen, and we'll get back to you. With that said, I'll hand it over to Copeland. Enjoy the webinar.
Yeah, hey everybody, thank you for joining. I'm going to take over and share my screen. All right. Oh, why didn't that work? Apologies, technical. Nope, why is it doing that? Okay, well, thanks for bearing with me. Here we are. And so today we're going to be talking about smarter wildfire datasets by pruning redundancy and fixing labels within the 3LC dashboard. Why is everything? Okay. So first I wanted to just give a brief overview on 3LC and what 3LC is. And so 3LC is a platform that we have built to support the data-centric approach to machine learning. What we've often found is that the quality of information obviously is the most important factor in driving performance within a machine learning model. The first thing I want to mention before I get into the tool is that 3LC is not a SAS. It is a Python package, literally a pip install 3LC. And so that means that 3LC runs within whatever environment our clients are currently operating, whether that be locally or in the cloud. And crucially, this means that at 3LC, we never see any of the data. Everything stays within client environments, and so that data privacy concern is alleviated. So the second thing to talk about is the age-old axiom of garbage in and garbage out. And it's really the first rule that any computer scientist or data scientist learns within their computer science education. And what we've seen is that this concept is being overlooked more and more often within industry as organizations are opting for larger and more powerful models rather than understanding how the data and the quality of the data is impacting the way their models are learning. So at 3LC, we like to say that we are illuminating the black box of ML. And so we're teaching clients through exploration how their data is impacting the model and providing the tools to directly resolve issues within their data. So what we're going to be talking about today is we're going to be exploring the Pyroestis wildfire smoke dataset. And this is a dataset that I have pulled off of public data set that I pulled off of Hugging Face. That consists of about 30,000 images from the French countryside. And the idea is that these edge devices are capturing smoke signal for early wildfire detection and prevention. And this data set was labeled by a combination of volunteers as well as an auto labeling process. And we will be able to explore how potentially the volunteers, potentially the auto labeling process fell short in a lot of ways. And I just wanted to mention that this data set is, I think, extremely pressing and important to me. I did a lot of my graduate research on wildfire detection and am based in Colorado, along with lots of our US team, where wildfires are currently breaking out all across the state. And so as an overview of where we're going with this presentation, My face is blocking some of our stats. But what we're doing is the goal of 3LC and of what we try to do is have better results with less data in a smaller model. And so what we can see in this graph, which is representing MAP 50, which is just a common performance metric for object detection tasks, the higher the score, the better. And so this yellow line is a training run from a data set that I curated within 3LC of only 5,000 samples. And this gray line is an uncurated data set with the full 30,000 sample training set, obviously compared against the same validation set. Additionally, this gray line was trained on a YOLO medium model, where the yellow line was trained on a YOLO nano model. So what we're seeing is we see 11 percentage points of improvement with 1/6 the data, as well as 8 times fewer model parameters. So by intelligently reducing the data and resolving labeling issues, we're able to see increased performance much quicker and much more easily within the machine learning world. So how we're going to walk through doing that today is the first thing we're going to do is we're going to work on curating the validation set, because we obviously can't trust any performance metrics on an inaccurate or a validation set that is containing many errors. Within this first step, we're also going to show how I can intelligently decimate the data and reduce redundant frames that are drowning out more nuanced signal within the model. The second thing we're going to do is I'm going to walk through how we can use the 3LC no-code UI wrapper to explore our dataset revisions and iterations, as well as kicking off new training runs. And then the third thing we'll do is we will explore a few more dataset curation workflows within the training set as well. Okay, now that we've gone through that, why don't we dive into it? So what we have here is this is the 3LC UI, and what I'm showing right now is just an initial baseline run that I did. So I'm going to click into it, and what it's going to do is it's going to open the 3LC dashboard, which is really the location where much of the data science and exploration of data is accomplished. And so what we have here on the bottom is a variety of columns, and these are all different metrics that I chose to extract from the training run. So in this instance, I only extracted metrics from the 30th epoch, which was my last epoch for this baseline training. And I extracted a few other metrics of interest, but all of these metrics are fully customizable, and you're able to really explore whatever metadata is of interest within a given data set, which in a later run, I will extract a few more nuanced metadata aspects. So now what I'm going to do is we're going to pull up the image, of course, as well as the ground truth bounding box. So we see here an image with this bounding box overlaid on a smoke signal. So there it is. Oh, I'm actually going to want to focus on the validation set. So I'm going to create a subset table where now we're only going to look at the validation set. So we have the image in our ground truth bounding boxes. Again, an image with the bounding box clearly overlaying on a small smoke signal here. The thing I'm going to pull up on the next door to it now is the image overlaid with the predicted bounding box. So here we go. On the left, we have the ground truth bounding boxes, and on the right, we have the model predicted bounding boxes from our training run. And as we can see in this instance, the model does quite a good job of predicting. The bounding boxes may be a slightly different size, but in general, the model is capturing that smoke signal and has quite a high overlap with our ground truth predicted bounding box. However, as some people may have noticed, I'm on index 2 from our data set. And if we look at index 0, for some reason, I have a predicted bounding box on a clear smoke signal, but with no corresponding ground truth. For those of you who are not totally sure whether or not this is a smoke signal, what you see over the temporal steps is that that same region and that same smoke signal does become labeled further on, but for some reason in the first two time steps, it is unlabeled. And this isn't a gimmick or shortcut that I did for the demonstration purposes. This is just pulled directly again from Hugging Face, and this is index 0 and 1 in the validation set. So clear errors immediately within the validation set, which is again the set that we're optimizing all of our training around. So if we aren't confident in the quality of our validation set, all the other work that we do is going to be essentially useless. So within 3LC, it's really easy to quickly ratify these issues around missing ground truth. I can click on the predicted bounding box and accept this prediction. So I'm accepting one new bounding box. I click accept, and here it is. It shows up now as a ground truth bounding box. And what we see up here is I now have one pending edit. So I have one pending edit to the data set. And when I'm done with a curation round, I can commit my pending edits, and it creates a Git style revision on top of my initial data set. And that way I can track and follow along with the edits I'm making over time. And again, on the first index, we're also missing this ground truth bounding box. I can use a hotkey here and quickly add this new ground truth. However, rather than clicking obviously through every single image within the scene, going one by one, we can also use some of these metrics on this left to more intelligently try to uncover these missing ground truth labels. So the thing I'm going to do in this instance, which is one of our common workflows, is I'm going to focus on high confidence predictions. So we'll say 70% confidence predictions with no matching ground truth IOU. So these are bounding boxes that the model was confident in, but have no overlap with current ground truth bounding boxes in the data set. And as we quickly see, sure enough, we have another prediction that doesn't have a matching ground truth bounding box on a smoke signal. What we can do is we can quickly click through, and we notice that indeed all of these predicted smoke signals are corresponding to true smoke signals that were not labeled, whether that be by the volunteers or by the auto labeling mechanism within our validation set. So these are clear errors that we want to remedy. And rather than doing that one by one, I can also do that in a batch capacity. So I can say all rows that I'm currently filtering on, we're going to add these bounding boxes. So in this instance, I'm now adding 80 new ground truth bounding boxes. And what you can see here is I'm adding 80 alongside 21 existing bounding boxes, because some of these images have are multi-fire scenes. So I obviously don't want to replace existing ground truth bounding boxes, but we're going to add these new 80 alongside them. Click accept, and now I have 82 pending edits. The other thing I wanted to quickly show as well, if we filter back up to the top, on index 6, we have an interesting example that's another common pitfall that we often see within client data. So in this instance, we have our ground truth bounding box that is clearly identifying a small smoke signal, as well as a corresponding predicted bounding box. However, as we can see, the predicted bounding box is only about half the height of the ground truth bounding box. This is because the labeler was clearly labeling this disparate smoke signal towards the top of the box, which the model did not deem reasonable to capture. And what's interesting is if we actually click in and override the resolution to show 640 resolution, which is what YOLO models are trained on, we see that this disparate smoke signal essentially disappears, and the model is just focusing in on the concentrated smoke signal at the base of the fire. And so in this instance, we're punishing the model for not writing the bounding box around this very small smoke signal when it's really not a signal that the model could have ever seen based on the image resolution it was fed. And so this is an issue that we can remedy by, again, replacing the ground truth bounding box with instead the more specified predicted bounding box that is going to more succinctly feed the model the information and the true signal that it is required to learn how to identify these smoke signals. Okay, so that is a brief overview on how we can look at detecting missing ground truths or errors in ground truth bounding boxes. The next thing I want to do is I want to talk about reducing the data set intelligently, because as you can see quite quickly, what we have in this data set is essentially the same scene over and over again, one temporal step later. And so we're feeding the model lots of duplicate images. And so if I click out of, I'm going to go back to my full training set now instead of the validation set. So again, here is the image. And now I'm going to open up what I extracted here was I extracted the embeddings from the 30th epoch of the training run, and I reduced them to 3 dimensions with a UMAP reduction. And I'm also going to color these embeddings by confidence. So what we see now is that green dots are more confident predictions. And we can fly around here and we see that there's different clusters versus there's also independent samples kind of isolated. And so one of the things I can do is I'm going to lasso in on a specific cluster, grab this cluster. And what you see here is you see a cluster of largely samples that the model was quite confident in its prediction, as well as this cluster contains 205 images. And sure enough, this cluster contains essentially the same image over and over and over again within the data set. So we're passing the model 205 very similar instances with only small temporal changes. And what we can think about in this instance is the model likely only needs maybe 5 or 10 of these samples to understand the smoke signal being represented by this enormous temporal sequence. And by passing the model instead 200 of the same sample, we're not only passing it these redundant scenes, we're increasing training time, increasing training complexity, but we're also then hiding the more nuanced signal that might be represented by, say, these individual point clusters. And so what we can do is we can try to intelligently remove this data, these redundant scenes. And one of the ways that we can do that is I can derive a virtual column from the embeddings. So derive virtual column. There's lots of different columns we can derive. And in this instance, I'm going to derive something called the traversal index. And so as you can see, it now 3LC now generates a virtual column that I can again toggle on the left as well. And so the traversal index is a way that we can reduce the data. So if I say instead 100 samples, and so this is reducing and eliminating samples from the pool while retaining as much variability within the n-dimensional embedding space. So as you can see now, with only 100 samples present, all of those clusters are essentially eliminated and all of the redundant scenes are removed. And so within my iterative process of trying to improve this data set and improve model performance, I tested a number of different decimation options. And what I found, if I now click back to my no-code UI wrapper, is this 5K baseline. I found that with 5,000 samples, we see essentially equivalent performance in the model's ability to perform on the curated validation set as with 30,000 training samples. because again, we're removing those redundant scenes and we're making the more nuanced smoke detection signals more easily identifiable by the model. This was an iterative process. You can see here, 1,000 baseline clearly was not enough information for the model to understand how to recognize smoke within these complicated multi scenes. So the other thing I wanted to show now is we've been talking about these data set revisions and how we're editing data. And we can look and we can click into this dataset tab. And these are all the revisions that I've made on this dataset over time. And so this was actually the first dataset that I ever worked on in 3LC when joining. So as you can see, I made lots of revisions, tried lots of different things, and explored lots of different tooling within 3LC. But I can click back in on any one of these revisions and see what I was working on at the time. But what we're going to do down here is I can grab edit a table, validation final. So this is my final curated validation table. And way over here, I have 5K unedited. So this is the reduced to 5,000 training samples, unedited data. And if I right click and click on our YOLO plugin, I can load this YOLO plugin. And then what I can do is I can immediately kick off a new training script. We'll call it Fire Demo with these new curated data sets. So all of this work can be done through the Python APIs, but our UI wrapper here is just trying to make that process more streamlined and easier for users. So now I have validation. We can swap these. So we have my train table, my validation table. I can select different models, different epochs. I can determine some of the metrics I want to collect, at what frequency I want to collect, and then I can kick off a new training run. And when I kick off this training run, it'll show back up here, and you can kind of dot follow and watch as it progresses along. The other thing that I wanted to show within our 3LC hub, this UI, is actually if I click in here, so this is a run that I did before curating the val set, initial, and I could run on this Insights tab. And what this Insights tab does is it performs statistical inference on your data set. So this isn't AI, this is just good old statistics, and it'll give you a score on how it thinks the data set currently, the quality of the current data set, and it'll identify some possible issues within the data set. So as you can see, before curation, the validation set is not particularly strong. The statistics indicate there's probably object size outliers. And I can click down here and I can open this object size outliers workflow directly back in to the 3LC dashboard. We see a high false positive rate, issues with IOU on true positive. So these are some of those issues that we addressed already. But for now, I'm going to go back into our decimated, smaller 5,000 sample data set, and we can explore this object size outlier issue as well. So that was a clear issue within the auto labeling of this data set. So if I click open, we're going to open back in, and now we're back in our dashboard. And this time, we're now just looking at our decimated data set. But what I will do is I will re-pull up our image with our overlaying ground truth bounding box. We have a smoke signal here detected. And now I want to explore those object size outliers that the Hub Insights indicated might be an issue. So what I'm going to do is I'm going to derive another virtual column like I did with the embeddings traversal index. This time I'm going to derive a virtual column from the ground truth bounding box. So derive virtual column, lots of different options, but what I'm going to do is I'm going to look in, I'm just going to go the area. So I just derived this pixel count area for ground truth bounding boxes. And on the left here, you can see most of the bounding boxes are clustered down here. But if we toggle up to where these larger bounding boxes are, we see quickly clear errors that present themselves. So in this instance, we just have some sort of cloud formation moving through. And so we can go ahead and delete these issues and go through. And now we have most likely an auto-labeling issue where clouds and the reflectance off the water are incorrectly labeled, again, as a ground truth within the training set. Obviously, this is not a sample that we want to be teaching the model to label as smoke. So we click through and we can delete a lot of these different issues. In this instance, I think it's snowing, or some of these it's snowing and the snow clouds have been for some reason labeled as incorrect ground truths. Down here we have some sort of camera malfunction, or maybe there's something on the lens. And again, for some reason, this has been labeled as a ground truth wildfire. Definitely not something we want to teach the model. So we can go ahead and delete these. I am seeing some questions pop up. I'll answer questions at the end. Apologies for not touching on those earlier. Another issue that we saw based on those clouds, I'm going to go through this quickly, we're running out of time, is I can derive also virtual columns based on the location of bounding boxes. And so now I'm trying to isolate bounding boxes towards the top of the scene. And in this method, we can see, again, a lot of these instances where most likely the auto-labeling process incorrectly is identifying clouds as smoke. So we definitely don't want to be teaching, again, we don't want this signal to be passed to the model that this is what smoke looks like. So we can go through and iteratively remove these. And just as before, this creates pending edits. The last thing I want to mention before I open this up to some questions from the audience is one of the things that I noticed within this data set specifically was the model was struggling on multi-fire images. So if I filter my ground truth count to 4 or 5, what we see is a lot of these scenes where fires have broken out throughout the scene. And because the model was really struggling to detect all of these bounding boxes, one of the things that we can do is we can actually upweight the value of how often this scene is going to be sampled within the next training run. So, I can change this to 2, and now next time when I retrain, this image is going to be sampled twice as often within the training run and really focus the model on how it can identify these multi-fire scenes. And similarly as before, I can do this in a batch process. I can tell it I want all of these to be actually upweighted at 2. We really want to focus in on these multi-fire scenes. Before I open it up to questions, the last thing here is I also did, like I mentioned earlier, I captured more metrics in this instance. I captured which camera the scene was taking from, what time of day it was, to try to identify if some of these other metadata components could help teach me if there was a specific instance where the model was often failing. All right, and that does conclude the demo. And I want to also mention that I did end up curating the full data set, and I published that to Hugging Face as well. So I curated the validation set, I pruned it with embeddings, and I fixed many, many labels, and I published that on Hugging Face. So I recommend anybody who's interested to go ahead and explore the curated Pyro Estes data set. I'm sure that more errors that I missed can be found there. But otherwise, thank you for listening. I encourage everyone to try the data-centric approach to machine learning on their own data and explore how they can more intelligently feed their model what they need. Feel free to reach out to myself. My email and LinkedIn is on the screen now. Or again, click the link to book a meeting with 3LC. And let me now see what kind of questions might have arose. So I had a question about what each point represented on the UMAP. So in that instance, that was just a per image. So that was every image from the 30th epoch was 1 point. And that is something that is also quite customizable. So I could have extracted per bounding box embedding representations, as well as embedding representations throughout many different epochs, which is also often a helpful workflow to see how samples are moving throughout the training period. And oftentimes you have more challenging samples tend to move a lot across the embedding space, whereas easy to recognize samples stay pretty stagnant throughout. All right, let's see. Have I tried using the SAM2 models? Yeah, so SAM2 models, that's something that we definitely support. And that was actually one of the ways that this data set was auto-labeled. And some of those issues that we were identifying just now were related to SAM2 mis-auto-labeling. But that is a tool that we support and a plugin that we have, and definitely something that we see a lot within our clients. I'm wondering how you define false negative versus false positive on the rows. Yeah, so those are evaluated based on a IOU threshold. I think in that instance, it was probably set to 0.5. So whether or not there was at least half overlap with ground truth and predicted bounding boxes. How do you visualize the images in the dashboard with the resolution that YOLO accepts? Yeah, so if we right click on the image, you can toggle based on resolution. And that obviously requires that you know the resolution that your model was trained on. Often models are trained on a variety of resolutions, but that is something that is established within the training script when you initially kick off the model. So when I was showing kicking off a new training run, the default for YOLO is typically 640 resolution. Other models are trained at higher resolution as well as lower resolution, but it's just a neat trick to explore what the model can actually see. And it's often something that we overlook as data scientists and are confused on why these smaller signals might be missed within the model. Well, I appreciate everyone's questions, and thank you for listening to our webinar here. This is our first time doing one, and appreciate the patience through some of the technical challenges. But any further questions, I definitely recommend people reach out to myself or to 3LC in general. Oh, again, my photo is covering our scanner, but please reach out, and I wish everyone luck in exploring their data set through the 3LC data-centric approach to machine learning. Thank you all. Enjoy the rest of your day.